Example number 5. Now let's talk about how we can solve the linear system. Okay. So like this is homogeneous linear system with constant coefficient, right? So in this video, I will show you how we can solve this linear system. Okay. But I'm not going to show you the how we can generate the trajectory of the system. Okay. But like I will talk about this one in class. Okay. In class, I will show you how we can draw the direction field. Okay. But in this video, I'm going to show you how we can solve this, okay? As we just discuss about this one right before in this video, and it is exactly because of with finding eigenvalue and eigenvector, okay? So the process is really easy. We're going to, first of all, we're going to find eigenvalues. Then we're going to find eigenvectors corresponding with eigenvalues. Then with that eigenvalue and eigenvector, we're going to set up the fundamental set of solution. Okay, that's it. Okay, let me start. And 1, -2, 3, -4 is the vector A. Let's say it is vector A. Then we will try to find eigenvalue of this vector. Okay, I mean this matrix. I'm sorry. Okay, here we go. How can you find it? We're going to set the determinant A minus lambda I equals 0, okay? A minus lambda I is 1 minus lambda minus 2, 3, and -4 minus lambda, okay? As you know, like it's 2 by 2 matrix, which is AD minus BC, okay? 1 minus lambda times -4 minus lambda minus BC must be equal to 0, okay? From this one, you will get the quadratic equation, okay? -4 and +4 and -1, which is plus 3 lambda and lambda square, and this is 6. Okay, let me rewrite this one in order. Lambda square plus 3 lambda plus 2 equals 0. That's really perfect. That's really easy to factor, right? Here we go. Then I have 2 eigenvalues. Let's say lambda 1, which is -1, lambda 2 is -2. Then now, like for each lambda, which is eigenvalues, we're going to find corresponding eigenvectors, okay? Let's start from -1, okay? Okay. The first one, the lambda 1. Then we're going to do this one, okay? A minus 1I V equals 0. It's okay? Then it is A minus or plus 1, right? So 1 plus 1, 2, minus 2, 3, -4, minus 1, which is -3. And let me write the elementary form, V1, V2 equal to 0 and 0, okay? Then when you multiply this one, is like 2V1 minus 2V2 equals 0, or 3V1 minus 3V2 equal to 0, right? But keep that in mind, they are same thing, okay? Then I can say this V1 is V2, because it makes sense. Then I can say my first eigenvector V1 is 1, 1. Okay, like you understand what I'm saying, right? That's it, okay. So what about the other guy? And that which is -2 case. Then we will do the same thing. Since I don't have enough space, let me like this way. Okay. Then it is A plus 2. A plus 2. There we go. 1 plus 2. 3, -2, 3, -4 plus 2, -2. And V1, it always happened this form, okay? Then again, like they are exact same thing, then we can say 3v1 minus 2v2 equals 0, which means 3v1 is equal to v2. Does that make sense? Okay, so if I say v1 is 2, then your v2 is 3, right? So we can say the second eigenvalue is 23, okay? And that's enough, okay? But keep that in mind, your lambda, which is eigenvalue, is concerned with the power of exponential function, right? So there we go. Let me combine these two. I need a little more space. Give me 1 second. Okay. We can combine like this way. My solution matrix xt is equal to coefficient c1 times e to the first eigenvalue, which is -1, minus t with eigenvector 1, 1, and c2 times second eigenvalue, which is -2, times eigenvector. That's it. Okay. So well, like even like I'm not going to show you the trajectory in this video. I can tell you like the behavior when t goes to infinite, right? It's really easy, right? When x goes to infinite, t goes to infinite, what happened? E to the minus t will go to 0, and e to the minus 2t is also go to 0. Then I can say my source t goes to 0. Okay. And like in the class, I will show you how we can draw the like trajectory, okay? And we can see the, like this behavior with the trajectory, okay? Thank you.